Thank you very much. Very, very kind introduction. But probably Marek already mentioned the main part of my talk. So let me talk about a little bit more detail. The title is What is Quasi-Variational Inequality? Well, my plan of my talk is 1, 2, 3, 4 topics. And this is a very small part, a joint work with Marek. We started our cooperation since almost 30 years ago. Okay. First section is, the title is, Why is the variational inequality concept necessary? Now, of course, I know that everybody understands, everybody knows the importance of the variational inequality concept in the classical sense. But in my talk, let me explain it from some different point of view. Well, let us consider the usual parabolic diffusion process. And the first one is the parabolic equation with nonlinear source term and homogeneous Neumann boundary condition and initial condition. Many people treated this kind of initial boundary problem for nonlinear, semi-linear partial differential equation. But the most of interesting phenomena in the real world, and many, especially many modelings arising from material and biological sciences, we need some additional condition, probably comes from the physical requirement or environment requirement. And you know, this system itself already well posed. But as I mentioned, we have to additional constraints. For instance, the state of the process should be some confined, some controlled set. Here is K, P of T, is a closed and convex set in usual. H is in our case L2 or the usual Sobolev space H1. For instance, this convex constraint set is a typical example. Just the gradient constraint. P is a given function as a parameter. Probably in this case, the parameter space X can be chosen, well, something like continuous function space over Q. Okay. Well, from realistic real-world problem requirement, we have to this system with this kind of constraint. But you know, this is over conditional requirement. So the system D, B, I, and C is not mathematically complete. Yeah, I mean that these systems in general has no solution. This one is an overdetermined condition. So now, but if function U satisfy this system with constraint property C, then we multiply the test function U minus eta, the parabolic equation, by U minus theta. Then you have this kind of variational equality because we have U satisfy the equation exactly. But when you replace this equality by inequality, this one automatically satisfies. Of course, in this case, the test function eta chosen from the constraint set. And furthermore, you use the integration by part this term to this term. This term divided into three parts, this one, and this one, and this one. So we have this variational inequality, which is called the weak form of the variational inequality from this one. So we have immediately from the strong form, the weak form. In this case, the test function eta should be integrable in time. And in the weak formulation of variational inequality, in general, we don't require the, just we require the less regularity about U. So just continuous. Now, of course, this U has to satisfy the state constraint, of course. Okay. Well, we know that under this regularity condition for the solution, variational inequality is well posed. And also, under this weak regularity condition, this weak form of the variational inequality is also well posed. So, the system can be treated as variational inequality over its weak form because these ones are theoretically complete and well posed. Okay. In our discussion, this weak form of variational.
No, just a question. But of course, it means that you don't have equivalence between these problems.
If you have this regularity property, weak form is equivalent to the strong form.
To the strong
yes.
form, yes.
But the main point, we don't require this, only this one. We don't require the differentiability of time. Because this one is so strong to apply the real world problem.
But I don't understand one point in your definition. Yes. Namely, if you have U belonging to the set K, yeah, the convex set of constraints,
yeah,
and eta belonging to the set K,
yeah, eta also
belongs to the set K.
Yeah,
so
yes, yeah,
and
of course.
Then U minus eta belongs to the set K only if it has a conical form.
No. This is just convex, not linear.
Not con, yeah?
Yeah,
no,
this is just convex set.
It's only convex.
Convex, only convex.
Then U minus eta doesn't necessarily belong to K.
No, it's not necessary.
This is just a test function.
Okay. It's convex, not conical, and this U minus eta in this reformed formulation doesn't satisfy constraints.
No.
Okay.
Nobuyuki, one perhaps interpretation point. This kind of weak variational formulation gives direct access to computational approximations of the problem. So that's one of the justifications why this sort of procedure is applied. Because in an approximate sense, you can resolve these problems in their finite dimensional approximation.
Yeah, of course, of course, the weak formulation approximated by strong sequence of the strong solutions. Actually, this solution is a limit of the strong solution, strong formulation solution. But we don't expect any convergence in this space. Just we have convergence in this space. So the solution of weak formulation variational inequality has a just continuity.
No regular.
Theoretical,
regular.
Yeah, theoretical.
Mm-hmm.
But interesting point is we report that is unique. Solution is unique in the weak class too. Okay. Now, main part of this my talk. What is quasi-variational inequality? So probably, I guess that many people, in connection with the variational inequality or its weak formulation, we want to consider closed loop system. That is, how to determine the parameter P as some condition, some property require satisfied. In a sense, this is some control problem.
So the control is to be understood in the sense that solution of the state of the system U will satisfy the constraint, and it is the objective to determine P a control variable so as to guarantee that this happens.
Yes, exactly. So you start some state, but of course you are very lucky. You have immediated this situation, but in general, you repeat and repeat many times. Finally, you get this situation. Okay, so what is our quasi-variational inequality? That is the concept of quasi-variational inequality is the following. Quasi-variational inequality with feedback system lambda or its weak formulation is formulated to be the problem. Variational inequality or its weak form plus feedback relationship P is equal to lambda of U. So more precisely, we say that a couple of the function U and the parameter P is a solution of quasi-variational inequality with feedback system lambda, the weak form in our case, is that U is a continuous function from the interval into Hilbert space H, in this case L2. P is the including one parameter, and the state is the included in the constraint set. And this variational inequality folds for any test function eta, initial condition, and P is equal to lambda of U, the feedback relations. And look at this variational inequality. P is lambda of U. So this constraint set depends on the unknown, actually. Such a variational inequality is called quasi-variational inequality. Namely, variational inequality with unknown constraint set.
Actually, with feedback. Constraint set is known, but feedback.
In this sense,
But well, we want to say that the feedback system, but from the free boundary problem, we don't.
You know the feedback law, you don't know the exact constraint.
So we want just how to get this special kind of parameter. This is the question, because this gives the solution of many of the free boundary problems. Okay. So now let me give you a very concrete feedback operator lambda. Lambda is the mapping from this space into continuous function space. And by definition, P is equal to lambda of U if and only if actually a P naught of theta. Theta is a solution of a usual heat equation. And you have unknown U here in the source term. Now, of course, this is enough good parabolic equation so that it has a very nice solution, especially in the space of this. So in this case, we call the quasi-variational inequality with this type of feedback system. What is this? That is the problem to find a function u and theta. Gradient constraint property satisfied. But this one depends on unknown theta. And this variational inequality called and the heat equation satisfies the initial condition. Okay. This kind of, well, you consider this kind of very complicated system, it's very, very difficult to expect the strong solution. Probably there is no strong solution. But exists a unique weak solution. But of course, the full system, I mean, this system itself has no uniqueness. Each one is unique solved. Okay. So, next question is, how to approach to such a quasi-variational inequality in a convex analysis? Let me remember some very important concept about the subdifferential of convex function H be abstract Hilbert space and known and inner product. And now let phi is a convex function on H. The value this one takes the value maybe plus infinity, but not identically plus infinity, lower semi-continuous function in the extended sense, and convex. This is the effective domain on which the convex function takes a finite value. And by definition, Z star included in of this subdifferential operator at Z if and only if this variational inequality is satisfied. So, a concrete case, just the same variational inequality, which I mentioned already, we take as a convex function phi P, which is given this formula, the square gradient, the L2 norm, plus indicate a function of this convex set, which is defined this formula. Say Z is in the convex set K, Pt, the value is 0, otherwise plus infinity.
May I just make a very short interruption for some things that you consider obvious, but we should really make a clear point on them. First of all, we consider infinity to be a fully justified element of the extended set of reals, and so you qualify the constraint of either being satisfied, and then you have this indicator function equal 0, otherwise, if not satisfied, you have it infinity, and this gets projected into the subdifferential, which is a direct generalization of normal differential. And so the idea behind it is a simple extension of the traditional variational principle, which says that the differential is equal 0.
Yeah. Yeah.
And here, well, I just made it as a kind of comment.
Yeah, but yes, exactly. Very nice comment. But wow, the interesting usual case, this convex set has no interior point. So structure is very, very complicated. Everywhere boundary point. In this example too. But in any case, the subdifferential of this convex set, the Z star is an element in the subdifferential at P. By definition, this inequality is satisfied. So you take the first variation of this convex functional, you have this inequalities. But this one is formally, well, you have from this, you have a minus kappa Laplacian of Z plus this inequality plus the subdifferential of indicator function, just formally. If this convex set has an interior point, this is exactly this one. But in general case, no interior point. So this actually is just formally equivalent. We have to always this variational inequality should be considered. Okay. So now, let me introduce our abstract quasi-variational evolution inclusion. We are given a feedback system lambda and into some Banach space. And strong form, the quasi-variational inequality with feedback system lambda is given by this formula. Regularity property AC, absolutely continuous. Usually evolution inclusion is satisfied initial condition, and actually this convex function depends on the parameter P. So we want to special parameter which is just equal to lambda of u. And weak form is this variational inclusion, the strong form, is replaced by this corresponding weak form. In this case, we require less regularity for the solution U. This is our abstract quasi-variational evolution inclusion. Okay, just let me one theorem. Under some regularity assumptions for the mapping TP to a convex function, and some, this is very important, compactness assumptions on feedback system lambda, this weak form, the quasi-variational inequality, admit at least one solution. And well, so nobody understands this theorem saying. It's an important part is found in this part, and the sum regularity assumption, and the sum compactness assumption. You can guess, you can imagine in the concrete examples. Well, this is made, but let me skip this part. Finally, let me apply our abstract result to some partial differential equations arising in biological science. Well, let us consider a reaction diffusion system. Well, n species of bacteria. I denote it by vector function u. Each component denotes the density of the each one species bacteria.
So the population consists of n different species.
Yeah.
And you are interested in the evolution dynamics of this population driven by diffusive and chemical reaction mechanisms.
Yes. And well, reaction diffusion equation is, well, this is the vector valued description. So you can understand this equation. Each component is governed by this similar type of evolution equation.
But V here.
What?
So V is the velocity of the velocity, right?
Yeah.
Okay.
Yeah.
Well,
reaction.
But so, for instance, U1 here minus mu Laplacian U1 here, and V is the solution of Navier-Stokes equation, and so convection term. U1 here, and this one is well, F has n components. We have here the reaction term. This partial differential equation has n number of the n partial differential equation. But mysterious term is here. E of theta is environment constraint. That is the, more concretely, survival regions of bacteria. So this is the, well, given A of theta is given vector field with n components, every positive, but depend on temperature, theta, definitely. So this means this one is polyhedral, which depend on the space and time. So fixing the space variable and time, this one is polyhedral. Polyhedral changes depending on space variable and time. You see, that you have there are many bacteria. Each bacteria are very strong for the high temperature. Some of them are very strong at a lower temperature. So the survival region depends on the temperature, and each bacteria has the different survival region. Okay? But mathematically, the vector field A of theta is smooth. And well, second equation is Navier-Stokes equation. You consider the container, very big container. And in this container, there is a flow, fluid flow. And there are sea glass, or you can imagine biomass, for instance.
Navier, if you allow me, perhaps just to clarify, start thinking about biomass development. So you have the biomass composed of group, some different classes of bacteria, and in this big container you have a sort of fluid having a possibility of some flow, and then once the reaction happens, a kind of biofilm is created, and the subdomain occupied by biofilm, by biomass, gets fixed. No flow is admissible any longer in that subdomain. So, in a sense, the problem is that you have the question on how to represent the process of creation of this biomass that gets extracted out of the entire region.
Yes.
And you see this feedback. As biomass gets created, so a subdomain gets excluded. And this means that there is a coupling between the bulk processes in the bulk, and some geometric development.
Okay, so now time for a stupid question. Why can't we just make the viscosity depend on the bacteria?
This is a kind of relaxation, approximation to the model. You are right, this is the way some people do. This is a kind of approximation to the model. And
this is actually more real than saying that nothing can flow for bacteria.
No, but you are interested in bacteria, so you need this U saying telling you the concentration of bacteria, yes?
Sure. Sure, but we want to model the fact that when we have a biofilm in some place, there shouldn't be any flow, right? And here it's assumed that this flow is immediately disabled, as it was a solid rock. But usually it's not like that. If you just have some concentration of mass, it gets harder to get pushed or to get flow, but it's a continuous process from here.
You know, Miron, this is related to the kind of approach which is based on postulating an existence of effect called free boundary. So that's an approximation. You assume there is an interface, a short interface, if the regularity were sufficient, between this domain where still you have a flow and biomass. And your approach means that there is a kind of layer in between, allowing for some smooth transition from one to another region. So these two approaches are in a sense complementary to each other, and you can apply either of those, but eventually you come to the question on how to get a kind of limit passage between these two formalisms. So it's you can go both ways. Your approach is in a sense as if going to scale from the very beginning, admitting for this critical region to exist where driving forces should be governed by a kind of different mechanisms from lower scale.
You can use a more sophisticated Navier-Stokes with a tensor of viscosity.
You see, this is a kind of prototype, yeah, okay. Certainly.
Yeah, well, where we consider the biomass, sometimes, some cases, biomass almost crystal or very rough, like sea glass, so porous medium. In this case, in the biomass, we have zero flow. But in the crystal, there is no flow. So many cases. Okay. Probably this system contributed in some sense to such a kind of biomass evolution equation. I believe that. And so, okay, so Navier-Stokes equation, we consider the just the gradient. For the velocity, we consider the velocity gradient constraint. They're very artificial. But nobody knows what happened in biomass actually.
So it's just a matter of phenomenological hypothesis.
I can say that it's a kind of simplification because you omit modeling, let's say, even a phase change in the system by saying that it's that we know how it will work, so we are making a meta model that will be actually a constraint.
Yeah, that's the approach to the this variational formulation.
Yeah.
And
okay.
We get a simpler equation.
Under such a constraint, we can solve the Navier-Stokes variational inclusions, something like this. Independent. Of course, all together, we don't. The couple of the system is very, very difficult to solve uniquely. But each equation can be solved uniquely.
In an iterative process?
Yes, yes. So the, in a sense, we can compute step by step. First, given the other data, we can solve uniquely this one. And by using this solution, we solve the secondary this Navier-Stokes equation, and thirdly heat equation, and go back the first one, iterate. And each step can be solved uniquely. This one is guaranteed by our abstract cell. And finally, we can show that this system has at least one weak solution.
As whole, as the entire system.
Yes. Well, so yes, so finally, thank you very much for your attention. And
if I may add still one comment to this, you should, perhaps we are due to tell you this being seemingly the very first attempt to approach this kind of coupled system, accounting for all of these phenomena in a single model. You can refer to existing literature on individual components, but the system as complete structure has not yet been addressed to our knowledge by anybody. So certainly, Miron, you are right, modeling-wise, it is rather simplified. Still, it is just a kind of an indication on how to approach the challenges that are very well known in biotechnology. Still, there are, to our knowledge, no rigorous modeling treatments until now. So, in this connection, the kind of models that are necessary to be treated don't fit into any variational framework. You get into this loop, additional loop, that is necessary to handle the complete phenomenon. And the idea behind it was just to start the process of addressing coupled phase change phenomena, flows, over variable domains, and dependent upon the phase change percent.
Yeah. So actually, Zuza and Krzysiek are working on a project about regeneration of joints. It's basically more or less the same idea.
We got Krzysiek here, so we can.
No, it's here?
Yes.
But you see, the issue is
there are also in a model biomass.
The same problem here.
Yeah,
because
the idea is the same.
But the problem is that you have cells that are going to let's say repair the joint, and they are working in a flow, and they have to be incorporated inside a strict structure, and it should become stiff and have some properties. There's also a problem because it gets polarized, because let's say at first this structure is not polarized, and so it's weaker, and in time it gets polarized because it gets redissolved and reconstructed by a specific cell. So there's also this field of polarization is important. So here I think that the problem with modeling this, and the problem why we are probably going to surrender on a very small and simple model, is that it's an extremely many-scale problem, because the joint is huge compared to the cells that operate on it. And and there is also some mechanical problem. It gets stressed. You know that stress in this structure makes its repair faster, so there are problems like that. So you may probably...
Yeah, but you see, the issue is, this is by far further stage of development, as no rigorous mathematical foundation is available for this model. And then what they do in modeling is simulation, computer simulation.
You represent simply simulation approach, and he represents mathematical foundation approach.
Well, I know, but remember that there is a very good reason to do this, because they say that they have a good numerical method to do this, and we also don't have to.
But I am interested in something else. Certainly, Professor Miezgutka will tell us something about computational conclusions from these quasi-variational inequalities. But I want to give one comment to this idea. It was with the concept of sub-differential, and if it's not satisfied, that you admit plus infinity as a value of it. It's an old trick, very often used in mathematics, and in computational approach, it represents penalty function. So you assume that, okay, violation can occur, but you are heavily penalized for that. And if this penalty function gets steeper and steeper, you get almost precise solution. That was done many times, and also very good mathematical theory was developed for that.
I think.
So this is exactly the idea. When I mentioned the reference to the availability of computational approximations behind all of this.
Yeah. I think that penalty method is, sometimes penalty approach is a much larger idea for this one. But in almost the cases, it's very difficult to prove convergence of the penalty term.
Yeah, that's the question, basic question in penalty approaches, mathematical question. Yeah.
So, I must say that for me it's a bit connected to my first question about the more sophisticated viscosity, because I feel that if you start to add first change let's say more continuous problem to a more discrete one, and then you try to solve the problems caused by the discrete problem by applying another continuous problem, it's maybe better just to go back and try with this continuous model at the very beginning and to try to solve it rather than try to recreate it in a different problem which may apply some different assumptions. And obviously mathematics loses less things than computation, but it may be still.
But back to your question, it's very well justified. Again, the answer is quite similar, namely, by introducing a kind of viscosity approximation model, you get much more regular.
But you know, it's not approximation.
Well, it's question what approximates what. That's really true. In any case, mathematically it's an approximation. And it simply hides the existence of additional scales of resolution. And but the very fact is that the viscosity approximation eases mathematical treatment of the problems, so you get more of on the existence, sometimes uniqueness of the solutions. The real challenge, and it's not me, it's Nobuyuki, who is extremely experienced with this. The challenges to prove any convergence.
Well, the problem with me is that I'm a physicist, and
Yeah.
physicists are, in this point, different from mathematicians, that they believe that something like physics exists, and this is a magical one that removes all the trouble with existence, with uniqueness, because if something is physics, it's probably solvable, and it's probably solved in only one thing.
I believe I can answer you.
So if you go
I
into
believe I
physics,
can answer you.
Okay.
It's clear that when we simulate something called computers, we have always some solution. The question is, if you have an iterate procedure, what will be the limit? And in what sense it will be the limit? That's the oldest problem in mathematics. And Banach, for example, has shown that there are spaces in which the limit doesn't exist. So we must be first sure what properties.
Those spaces don't exist in computers. So it's
but can lead us to wrong conclusions from computers.
Obviously.
No, but you see, this is actually real good luck, I would say, that in this discussion we have got a confrontation of at least three different points of view. A point of view of mathematical foundations that guarantee that what you do then computationally is in some sense viable. Your physical viewpoint, based on the intuition resulting from experimental knowledge and some concepts that point-wise are well justified, but if you aggregate them into a kind of composite setup, you lose the understanding of the
or even you can get chaos, for example.
And your point of view, namely the point of view of somebody originating from control theory and from computational control theory. Yeah. So you see, but then we got into the point that some type of computer simulation is being prepared for biomass phenomena, and that we got also somebody who has developed a very advanced computational machinery to resolve this kind of large-scale problems. So, in a sense, this meeting, and I would be glad if we just conclude with this, identified the sort of synergy that potentially may emerge out of this. Your modeling study, your computational stuff, and some, well, not to say about physics, but also some quite esoteric mathematical theory that goes far beyond commonly known range of mathematical tools.
No, but note that applying this to the Grzesiek's problem is actually going into removing most of the computational part of his model.
No, not at all. Not at all. You know, the question, the reason is, you have not got this point. This theory can bring you only to the existence. You don't have uniqueness.
Yeah.
So, computational approach means a sort of selection of specific unique solution. It's a selection of a solution among those that do exist.
Yeah, the numerical point of view, each step, the procedure of each step uniquely determined. But altogether, the limit has no uniqueness structure.
So, if there are still any comments or questions, I think, first of all, we should thank Nobuyuki for this introduction. But then I strongly encourage all of you to recognize the office in the corner of this floor where Professor Kenmochi is doing his research and is very eager to meet everybody and discuss on specific questions and specific topics. As Miron mentioned, the very modeling approach is only one of possible ways to do so. But there is no reason for not attempting to go also some of those complementary ways that you have addressed. So again, and also the simulation study, just getting together means that this may result in a quite novel approaches and I think highly valuable publications. Thank you very much.
Thank you very much.